Okay, so what we're going to do is we're going to let W1 and W2 be in the set, right? So, of course, you wouldn't say all this because I'm trying to be explanatory as well as prove it. Be in the set. What set? Well, at least one person said in W. Well, W might have things that aren't in the set that we're looking at. The set that we're looking at is the image of V, right? See, image of V, not W. Which might contain vectors not in the image of V. Okay? So what's that mean? Well, for any vector in the image of V, there's at least one vector in V that gets mapped to that vector in W, okay? So we probably want to have names for these things. We'll say for any vector W in the image of V, there's at least one vector in V, and we'll call that vector V in V. Such that T of V equals W. Okay? So, we could let V1 and V2 be vectors in V. And T of V2 equals W2, right? Now you wanted to use inverse transformation to get your V1 and V2, right? And that was good, except that there's no guarantee that the transformation is 1-to-1, so you don't necessarily have an inverse transformation from the image back to T, right? You might have an inverse relation, but there might be an infinite number of vectors that map onto either of these. And matter of fact, in general, there will be. Unless your null space is empty, there will be an infinite number, because if V1 maps to W1, so does V1 plus any member of the null space. Right? And you have to understand that. And since your null space is generally an infinite subspace, maybe just one-dimensional, but still infinite, you understand that the pre-image of anything over here could be a whole affine subspace of V, and we haven't talked about that, but just a vector plus a null, vector plus a subspace. Anyhow, there you got it. So see what you can do with that.